Okay, a video then on the complex roots of unity. So this is essentially the roots of the number 1. So what complex numbers satisfy x squared equals 1? What complex numbers satisfy x cubed equals 1? What complex numbers satisfy x to the 4 equals 1, and so on? In other words, what's the square root of 1, cube root of 1, fourth root of 1, fifth root of 1, and so on? Well, it turns out that there are exactly nth roots of unity. So if you're looking at the cube root, there are 3 cube roots of 1. The fourth root, there are 4 fourth roots of 1. 5, there are 5 fifth roots of 1. In general, there are nth roots of 1. So how do we go about finding those? Well, what we need to remember is that when you multiply 2 complex numbers together, you multiply the moduli and you add the arguments. So you multiply the moduli and add the arguments. So when we're rooting, we're doing the reverse of that. So we are rooting the moduli and dividing the arguments. Okay. Because when you power something, you are multiplying multiple times. And a multiple multiplication is a power, so therefore to undo that effect is to root. And multiple additions is a multiplying. So to undo the multiplication, you need to divide. So in this case, let's have a look at x squared is 1. Now we know that the square roots of of 1 are 1 and minus 1. Okay, they're both real. Let's just have a look at the argument of 1. Well, that is 0, because it's a positive real number. So the argument of 1 is 0. So when we divide by 2, the argument of the square root of 1 is going to be equal to 0 over 2. But you could also have pi. Because, yes, 0 is an argument of 1, but actually there's also 2 pi and 4 pi and 6 pi and 8 pi. And in fact, any even integer times pi is an argument of 1. It's not a principal argument, granted, but it is an argument. So if I take 2 pi as my argument of 1, then when I divide it by 2, I'll get pi. If I take 4 pi as an argument of 1 and divide it by 2, I get 2 pi. But the argument of 2 pi is just the same as 0. So actually, I'll get back to this one again. 3 pi would give me pi. 4 pi would give me 0 again. 10 pi would divide down to 5 pi, which is pi. And I keep flip-flopping between these two. So there are 2 principal arguments for the square root of 1, namely 0 and pi. This explains then that 1 square root of 1 is equal to cos of 0 plus I times sine of 0, which is 1. And the other square root of 1 is equal to cos of pi plus I times sine of pi, which is minus 1. You end up with the 2 square roots. Cube roots then. Well, the argument of 1 is still 0, but now the argument of the cube root of 1 must be 0 divided by 3. But don't forget that actually 2 pi and 4 pi and 6 pi are also arguments of 1. So I need to take these and divide them by 3 as well. By the time I get to 6 pi on 3, I'll end up at 2 pi, which is the same as 0. So actually, I have, in this case, 3 arguments for the cube root of 1. So therefore, the cube root of 1 could be cos of 0 plus I times sine of 0, which we know is 1. But it could be cos of 2 pi on 3 plus I times sine of 2 pi on 3. Cos of 2 pi on 3 is minus a half, and sine of 2 pi on 3 is root 3 on 2. So that is also a cube root of minus 1. And the other one, if I plug in 4 pi on 3, I'll get minus a half minus root 3 on 2, I. Because just like any polynomial equation, which is what this is, any complex roots must appear as a pair of complex conjugates. Okay, so my three cube roots of 1 are 1, minus a half plus root 3 on 2i, and minus 1 minus root 3 on 2.